Okay. Oh, it's on. Great. Okay, welcome everyone. Let's get started. It's 3:30. So welcome everyone to the last talk session of today. Hope you're jittery with caffeinated energy. So our first talk will be by Jielun Chen from Caltech about tensor-network contraction. So take it away.
Hi. Okay. Hi everyone. Thank you for the introduction, and good afternoon. My name is Jielun Chen from Caltech. Today I will talk about how positive bias can make tensor network contraction tractable. This is joint work with Jiaqing Jiang from Caltech, Norbert Schuch from University of Vienna, and Dominik Hangleiter from Science Institute at Berkeley. So tensor network is a graph where each vertex has an associated tensor. For simplicity, let's focus on a 2D square lattice graph. Specifically, each edge can take values from 1 to d, where d is called bond dimension. And each vertex is associated with an order 4 tensor, which shares edges with nearby tensors. We define an edge labeling as an assignment of values to all edges in the graph. For example, this is a specific labeling where I, j, k, l, and all other edges have taken specific values. Then the contraction of a tensor network yields the contracted value, which is defined as the sum of products of tensor values over all possible edge labelings. Here, m sub to the c to the power of v means that the tensor associated with vertex b has its corresponding indices specified by values in the edge labeling C. So contracting a tensor network is a common computational task with many applications. For example, most commonly, it is used to study many-body physics, where the tensor represent virtual Hilbert spaces to capture entanglement structure. It also has been used in simulation of quantum circuits, where tensors are quantum gates, as well as computing classical partition functions where tensors are expansions of local energies, and other examples include counting inferences and so on. So despite of the importance of the tensor network contraction, rigorous statements are rare and often negative. It was proven that exact contraction of 2D tensor network is worst case sharply hard by Schuch, Wolf, Verstraete, and Sirac. And through the use of random self-reducibility, it was also proven to be average case sharply hard by the result from Hefferkamp, Hangleiter, Izard, and Kluza. Here, average case means that all the tensor entries are drawn from IID0 mean Gaussian distributions, and each tensor is independent from each other. The approximate contraction, while in many applications there are clever algorithms that work really well, if we think of a random tensor with random entries, then it is empirically hard. And there's a recent systematic study of this exact Gaussian ensemble by Garcia et al., which verifies that the standard entanglement-based contraction struggles on average for this type of tensor network. So our work identifies a new regime where approximate contraction is provably trackable classically in quasi-polynomial time, which is when the tensor network is slightly positive. So in other words, rather than having a zero mean Gaussian distribution, the mean is slightly shifted to the positive side. However, the mean is still much smaller than 1, as we will see. And additionally, the exact contraction remains sharply hard. So this talk will be focused on the quasi-polynomial time algorithm. So specifically, we show that for random 2D tensor network, if the mean is roughly greater than the inverse of the bond dimension, where roughly just means up to constant correction, and dimension is roughly greater than system size, then with high probability, there exists a quasi-polynomial time algorithm which approximates the contracted value up to arbitrary 1/Pauli multiplicative error. So the motivation for studying this question is to answer rigorously about a folklore statement, which is that the positivity can make tensor network easier to contract. So more specifically, there have been numerical observations that the complexity drops significantly when the tensor network is only slightly positive. And there's a phase transition in terms of entanglement versus non-positiveness. And in particular, Gray and Chen first observed such transition. And in a recent paper by us, we studied more systematically and have predicted the transition point. And the threshold in our result, in fact, matches the phase transition predicted in the latter paper. And even though the contraction method is completely different. So now I will give an overview to our method. So the high-level idea is to interpolate from an easy-to-contract tensor network towards the hard one we care about. So the easy case corresponds to the infinite mean case, and the endpoint of the interpolation is when mu equals to 1 over bound dimension d, which is the threshold we talked about. And let's just say we don't care about the case after this for now. And to see why it is easy when mu goes to infinity, we observe that a random Gaussian tensor with non-zero mean can be separated into two parts. So the first part is an all-one tensor, and it's thus a rank 1 tensor, and it's factorizable into four components. And the second part is the zero mean Gaussian tensor. So when mu goes to infinity, all tensors are simply replaced by the all-one tensors, which is easy to contract because it factorizes into simple products of numbers. So for convenience later, we introduce a change of variable, z equals to 1 over mu times d. And we also rescale the tensor by 1 over the mean, which actually has no effect on the multiplicative arrow. So now the tensor is under this new definition where the variable z is now associated with the zero mean Gaussian tensor instead of previously where the mu is associated with the all-one tensor. So at z equals 0, all the tensors are all the tensors are the rank 1 tensor, and at z equals to 1, we have mu equals to 1 over d. So therefore, now our goal is to interpolate from z equals to 0 to z equals 1, and this is just for convenience. So to do the interpolation, we use the Barvinox method, which I will describe in details later. And this method relies on two observations. Firstly, we know that the contracted tensor network value is a degree d random polynomial on z, where here n is the degree n random polynomial on z, where n is the system size, and we denote this polynomial as gz. And secondly, the case derivative of this polynomial on z at z equals 0 can actually be computed brute forcefully in a time exponential in k. So to illustrate, let's just look at the fourth derivative, which is essentially all tensor networks with 4 non-trivial zero mean Gaussian tensors, with the rest of the tensors replaced by the all-one tensor, and then which is factorizable. Therefore, we only need to compute these clusters of size at most k exactly, which takes time at most exponential in k. And to see this, we can just apply the product rule of derivative. So now I will introduce Barvinox method in details. So this algorithm is originally designed to approximate certain permanence. The input is a degree n polynomial gz, where the only requirement is that the case derivative at 0 can be computed in a time at most exponential in k. As we have seen, these are essentially the two observations we just made in the last slides about random tensor network. And the output is G1 with epsilon multiplicative arrow, which is also our goal. So the algorithm starts by considering the log of the polynomial, which switches our goal from epsilon multiplicative arrow to epsilon additive arrow. Then we express f with its Taylor series expansion at z equals 0 and truncate up to term n, and output the expansion of it. And that's actually it. So one thing I didn't say is how to compute the derivative of f. But given derivative of g, we can compute the derivative of f with just standard calculus tools. So while this is a very simple algorithm, the effectiveness is not that easy to analyze. In particular, it depends on the location of roots of gz, which determines the analyticity of f and thus the quality of the truncated Taylor expansion. So in particular, if all the roots of GZ are outside the z equals to 1 disk, then we have a very small arrow. And specifically, we can take up to log n over epsilon terms, which in turn results in a quasi-polynomial time algorithm because the case derivative can be computed in a time at most exponential k. However, if there's just a single root of GZ lying inside the disk, then the arrow blows up. So we can actually relax the condition of requiring no roots at all to be not many roots. So for example, if the number of roots is independent of the degree of the polynomial, then we can actually interpolate along a root-free path. And there are two methods to do this. So the first method is by Barwinock, where one maps the disk of radius 1 into a smaller strip that connects 0 and 1 through another polynomial we call phi z. And this polynomial is easy to define and has a degree at most exponential in terms of how narrow the strip is. So if the circle doesn't have many roots, then the strip will likely have no roots inside. Then we can Taylor expand the log g phi z instead, which then gives us a good Taylor expansion. And the second method is by Alder and Maherban in 2018, where instead of focusing on the big disk, we can Taylor expand along a series of smaller disks. And this was termed as the algorithm make it analytic continuation. And if there are not many roots, then likely we can find a root-free path using sort of like smaller and smaller circles. So while both methods introduce some overhead, they don't change the quasi-polynomial time nature of our algorithm. So now I have seen all the recipes. Let's focus on the random tensor network. So to summarize, we have seen that about for Barwinock method, we consider the Taylor expansion of log of the input polynomial. And if there are few roots inside the disk of radius 1 around 0, we can find a root-free path, which results in a quasi-polynomial time algorithm. So for random polynomials, such as the random tensor network where we care about, we require that there are few roots on average, and then thus allow us to find a root-free path with high probability, and then a quasi-polynomial time algorithm that success with high probability. But how to bound the average number of roots? In Alder and Maherban's work, they used a tool from complex analysis. So where we can relate the number of roots enclosing a circle to the average absolute value on the circle in the complex plane. So this is called the Jensen's formula. And then we can also use an inequality from the same mathematician Jensen, where due to that log is concave, we can pull the log out of the integral and the expectation value. So what do we achieve by this? So just in short, the average number of roots can be related to the second moment of the polynomial gz. So therefore, if we can bound the second moment of the polynomial gz, then we have some bound on the average number of roots, and in turn resulting in a quasi-polynomial time algorithm. So what is the second moment of the tensor network? So firstly, we take two copies of tensor network, and the second tensor network is taken to be the conjugated version. And because all the tensors are independent from each other, the average can be just taken locally. So by a simple calculation, we can see that the average of two copies of local tensor has two parts. And the first part is associated with the all-one tensor, and the second is a delta tensor connecting indices of the two copies of tensors. And this is simply this example of Wick's theorem, if you like. But you can also just calculate very simply, because the expectation of product of two independent Gaussian distribution is 0, and the expectation of absolute value of a Gaussian distribution is 1. Then if we like how two adjacent sites interact, we observe there's a factor of d introduced depending on how many loops the configuration creates. So therefore, we can imagine after averaging, we actually have a new determinist tensor network with entries being products of powers of D and some components of Z in it. And here are actually all the possible configurations we can get. So just to summarize what we have achieved, this actually, the average tensor network actually represents the partition function of a 2D classical Ising model with local magnetic fields. And interestingly, when Z equals to 1, we actually correspond to no presence of magnetic field. And with this recipe, we can actually use a well-known solution from Onsager about zero-field 2D Ising model, and also its finite size version to derive an upper bound on the second moment of the polynomial. And more specifically, we can show that use this partition function solution, we can bound that the second moment is bounded by constant for the approximately smaller than 1. And thus, we can also argue there are only constant number of roots on average and get a quasi-polynomial time algorithm in the end. So finally, I will just briefly summarize 2 of our results, which surrounds the case where the tensor network is fully positive. So firstly, we show that approximating a fully positive tensor network up to multiplicative arrow, a very large multiplicative arrow is still can make hard. So here, very large actually means exponentially close to 1, so you can actually tolerate 100% arrow almost. And the second result is that we show that contracting a positive tensor network up to certain additive arrow is BPP complete. And in particular, the arrow is the product of one norm of each tensor, given the elder of the tensors. And we view the tensors as matrices. And this should be compared with the earlier result by Arad and Landau, where for arbitrary tensor network with arrow being product of 2 norm instead, it is BQP complete. So the 1 norm and 2 norm difference come from embedding tensors in a stochastic matrix versus in a unitary matrix. And with that, I will like to conclude with some outlook that I think is interesting. So firstly, whether we can prove the tractability with a constant bond dimension. So in the numerical observation preceding our work, they don't really require the bond dimension to grow with system size. But in our proof, because we in the Ising partition function, the bond dimension actually plays a role in sort of the concentration effect. So it is possible that so in our method we have this bottleneck where the bond dimension also have to grow with system size, and it is actually possible to relate the number of roots with higher moments as well. But then the statistical model we get is like more complicated, which is harder to analyze. So. I don't know how to resolve this yet. And secondly, whether we can improve the method. So for example, we can imagine we can run a so-called belief propagation algorithm for tensor network contraction. It's roughly, it yields like a best sort of rank 1 approximation to the tensor network. And so we can maybe imagine expand around the BP fixed point. And the other direction is whether we can maybe use better interpolation methods. And in particular, Barbanov method has some connection with cluster expansion, and we can maybe seek some direction there. And lastly, whether this method can be modified to be practically useful. So maybe one can introduce some heuristic component to the method. And that's it. Thank you.
So we have a few minutes for questions.
Thanks for a nice talk. In your previous slides, you mentioned some problem about, this stock MA hard problem. I'm wondering, can you say anything about the upper bound? Is in AM or something?
Yeah, I mean, it's like, it's roughly like approximate counting, so it's inside AM.
So could you think it could be you have like better upper bound?
I'm not sure. I don't think we have. Yeah.
In the beginning, you mentioned that the phase transition appeared at the same point, even though your method was different.
Yes.
Do you know of an example where the phase transition happened at a different point when the method was different?
I mean, we really only did two methods. One is the standard entanglement-based contraction. The other is this method. So both appear in the same transition. So I think it indicates there might be like an intrinsic complexity transition. So yeah, I think it's kind of intrinsic.
It's what I would expect from a phase transition point, right? Should be a property of the system, should be independent of whatever you're solving. It's the transition of complexity. So it should be independent of the method.
Yeah, right.
Okay.
I agree, yeah.
So hi, good talk. I'm wondering whether your results apply for arbitrary tensor network states or just restrict to 2D square lattice.
So the algorithm itself can be applied to general tensor network, but if you want to upper bound, then it's a little bit harder because if it's not like lattice, then you don't have this Unsingers solution for partition function. But yeah, this algorithm works for general geometry.
Okay, thank you.
I'm curious if you've given any thought to what the implications are physically for the types of states that you can represent with this type of approach.
So that's a good question, and actually we don't have much to say at the point. So in the other paper that we did, so numerical simulation, we have some thoughts on, like, for example, if you have a tensor network and then you induce some positivity into a tensor network, it may help some algorithm, and we have a sample application for like spin liquid, but it's kind of like yeah, it's not super clear to us if there's application.
Thank you.
Hello, thank you for the nice talk. I just wanted to ask, because the calculations that you did were easier because you're actually thinking about a random sample. Could you apply that to maybe matrix product operators and do something similar to almost SYK modelish or just Anderson localization type systems? Not at the localization phase, but maybe slightly away from the to the other phase, where you still have the random part. Would it actually help you in calculating those kind of things in 2D? As a new application, maybe.
Yeah, I would say the algorithm is sort of so the algorithm itself, it doesn't need randomness. It's can be applied to whatever tensor network we want. But if we want to say some regress, we have to consider the randomness. But yeah, so yeah, I'm not sure if there's any application in your setting. So yeah, but this algorithm can be applied to to the yeah.
Okay, thank you.
Let's thank Chris again.
Okay.
Thank you. And let's take 5 minutes for the transition. So if you want to switch to another room, you can do that. And we'll start at 4 o'clock.